Remember that the basis of analyzing a truss is the idea of equilibrium. The whole truss is in equilibrium, and any part of the truss is in equilibrium. And so that means you can zoom in on one joint at a time, make a free body diagram there, and solve those forces, and then move on. And this is the basis of the method known as the method of joints, because we're looking at one joint at a time. And I've given you in your class materials a Word document that lists these steps too, if you like to refer to that. So here are the steps. We'll draw a free body diagram of the truss as a whole. We'll figure out the reactions, just like a beam. We'll look for any members that don't have force in them, zero force members. Then we'll start with one joint that has no more than two unknowns, and we'll draw a free body diagram. Then we'll do a tip to tail, and then we'll go on to the next joint. And as we go along, we'll write those forces on our truss. That's called a force summation diagram. I'll show you what that looks like. So let's look at an example. We won't go through this whole truss, but I want to show you the free body diagram of the truss as a whole. So here's a truss. It's got some weight hanging down. This might be a truck or a locomotive actually sitting on the bottom of the truss, for that matter. And let's make a free body diagram of the truss as a whole. So this is what it looks like. With the truss as a whole, you just draw, this is a truss-shaped beam, so you just draw the truss-shaped beam. You don't worry about the bars inside. You just draw the forces and the reactions. So there's my free body diagram of the truss as a whole. Then I go on to the next step and I solve the reactions. Then once I've done that, I come back and I figure out the forces in each of the members. Let's look at another example. This one has one 2,000-pound downward force and one 2,000-pound sideways force. Also, let's notice that there are two support conditions. There's a roller over here at C, and there's a pinned connection over here at A. And you remember that a pinned connection has a reaction in both the X and Y direction. So when you make your free body diagram of the truss as a whole, this pinned connection has an X reaction and a Y reaction. The roller at C has just a Y reaction, and then here are the forces. And I'm not worried about that bar in the middle right now. I'm just drawing the free body diagram of the truss as a whole so that I can solve the reactions. Think about what this X reaction must be. If you've got one X pushing to the right with 2,000 pounds, this one must be pushing to the left with 2,000 pounds, right? And then you can use your equilibrium equations, sum of all moments equals 0, to find the other reactions. I want to step through with you an example of this truss that we're looking at. Last year, a student decided to make a drawing of this truss and work through the method of joints in this CAD drawing. So here is her drawing of the truss as a whole. So ignoring the bar inside right now, she was able to label this X reaction right away because sum of all forces in the X direction equals 0, 2,000, 2,000. Then she used sum of all moments equals 0 to figure out 1750 on one end. Then she used the sum of all forces in the Y direction equals 0 to figure out 250 at the other end. Oh, you know what? She should have written blah, blah, blah equals 0, blah, blah, blah equals 0. She's missed that 0. But you will put in your 0. So here's her figuring out the reactions. Next step, identify any zero force members. We haven't learned how to do that yet. We'll talk about that in the next class. I'll just tell you that this particular truss does not have any. Every member has a force on it. Okay, let's go on to the next step. We'll start with one joint that has no more than two unknowns. And we'll draw a free body diagram at that joint. Now, at this point, we could not do joint D because it's got 3 unknowns. So that's too many. We can't solve that one yet. But we could do joint C. It's got 1 upward force and 2 unknown forces. So here's a free body diagram of the joint at C. Now, let's solve those unknown forces. And how do we do that? Yay, tip to tail. So we draw our free body diagram. Then we take copies of those unknown forces and stick them together tip to tail, and we measure how long they are. If you are a math sort of person and you would rather try your hand at the calculator, what you could do instead of drawing tip to tail is you could figure out the X and Y reactions in each of these forces, add up all the X reactions, add up all the Y reactions, as we did earlier in this term. And if you take statics over in the engineering program, that is the way you will be solving this, because they don't use AutoCAD over there. But we do, and we use tip to tail. Okay, so we've drawn them, we've measured them, and that's how long those forces turned out to be. And now, as we go along, we add the things that we've solved to our drawing of the truss. This is called a force summation diagram. It's a diagram that summarizes what forces are on this thing. So we found out that this horizontal force was this number, and we write that number on our truss. We found out that the sloping force was this number, so we write that number on our truss. And also important is label whether each force is compression, C for compression, or whether it's tension, T for tension. And remember that in a truss, the bottom bar is always in tension and the top bars are always in compression, because this thing is basically a beam. So the bottom is getting stretched, the top is getting compressed. So C for compression, T for tension. All right, now we move on to the next joint that has no more than 2 unknowns. Well, now we can do joint D because we just solved this horizontal bar and we already know the downward pulling arrow. So here's our free body diagram at D. You know what? You could solve this without doing a tip to tail if you wanted to. You could draw a tip to tail and you'd just be making a rectangle. But you could say, ooh, sum of all forces X equals 0, sum of all forces Y equals 0, and you would find out equal and opposite 2000, 2000, equal and opposite 2333, 2333, and there's your unknown forces. Make sure you label which one is in tension, being pulled, and which one is in, oh, now, what is happening here? Why is this bar in tension? There's no compression in this thing. Yes, this bottom bar is in tension. It's being pulled. This vertical bar has a 2,000 pound force pulling down, so it must have an equal and opposite reaction pulling up, so it's in tension too. So all the bars and forces in this joint are in tension. That's just fine. Now we'll go on to the next joint with no more than 2 unknowns. So we just solved this 2,000 pound thing. We previously solved this sloping thing. We know the 2,000 pound sideways force. So the only one we don't know here is the other sloping bar. So we can draw a free body diagram of the joint at B. Here's her free body diagram. Looking through your paper towel tube, focusing in on that joint there. So there's the free body diagram. Now we can take those forces and arrange them tip to tail and find out how long is this unknown slopey force. Turns out, when you stick all these together, that one's not very big. Look how short that is. Turns out it's only 414 pounds. And turns out it's pushing up. It's in compression because it's the top bar of a truss. So there's 414 compression. labeled on our force summation diagram. So now we've got forces labeled on all of our bars. You could have chosen joint A instead of joint B because it also had no more than 2 unknowns. And had it been me, I probably would have chosen joint A. I just think it's simpler than this thingy up here at B, but that's just me. I like to go simple. So here's the free body diagram if you were going to A instead. Whichever way you go, you've got a force summation diagram. And when you solved your last unknown and you put your force on here, you are then finished. So this is your force summation diagram that you have been creating as you go along. Notice that as you move from joint to joint, you are in effect flip-flopping the arrows. So let's look at joint C here. There's its free body diagram. And this horizontal bar is in tension. So at C, it's pulling away. Now we'll move over to D. Get your paper towel tube, zoom in close. This bar is in tension still, so that arrow is pulling away. When you're at C, the arrow is pulling away. When you're at D, the arrow is pulling away. But when you're zooming in close, away looks like a different direction than it did when you were zooming in close over here. That's the way it's supposed to be. As you move from a close-up of one joint to a close-up of another joint, those force arrows will flip-flop. And look over here. Here's a free body diagram at A. Here's the free body diagram at D. Forces in tension pulling away. Forces in tension pulling away. But those arrows are flip-flopped when you look at the overall truss and think about what the arrows are doing. And likewise, this bar that's in compression, down here at joint A, this force is in compression, it's pointing towards A. Going up here to joint B, that bar is still in compression, it's still pointing towards, but now up at B, pointing towards means it's pointing upward. So flip-flop the arrows as you go from joint to joint. Now let's look at the 2 trusses that are in your assignment for this time. I recommend that you take this in small bites, so you could just draw the 2 trusses. You're going to do these in CAD. You could just draw the 2 trusses and stop there if you want. Or you could draw this first truss. You know enough to solve this one. And notice that in this truss, he doesn't give you any sizes. In fact, all he gives you is a 2,000 Newton force and some 60-degree angles. That's no problem because since these are all 60-degree angles, these are all equilateral triangles. And that means no matter what size you decide to make those bars, you're going to get the same answer. So I could make my bars 10 feet long, and I'd get my answer. You could make your bars 23 feet long, you'd get exactly the same answer. And someone else could make their bars 3 feet long, they'd get exactly the same answer. So pick whatever size you want. Follow those method of joint steps. First, draw a free body diagram of the truss as a whole. Then solve the reactions. Then start at a joint with no more than 2 unknowns. Draw a free body diagram. Then draw a tip to tail to solve those unknown forces. Then write those forces on your force summation diagram. Then go on to the next joint with no more than 2 unknowns. Now for this second problem, I recommend you just draw the free body diagram of the truss as a whole. It turns out that there are some zero force members in here, so we'll come back next time and solve those.